In order to understand the importance of water, we need to come back to this idea of a hydrogen bond. We talked briefly about hydrogen bonds in the last lecture. This will be a quick review. So water is a molecule that can form what are called hydrogen bonds. The reason that water can form these hydrogen bonds is because remember that it is a polar molecule. And you can see in this picture, notice this slight, so that little funny symbol there, that delta, that means basically a slight negative charge. Over here we have a slight positive charge. So because of the unequal sharing of electrons between oxygen and hydrogen, we have this polar molecule with the positive and negative side. So this water molecule here will become attracted to another water molecule nearby. This one has a negative side here, here's a positive side, and they're attracted together. That is called a hydrogen bond. Hydrogen bonds are very important to water and to make water what it is. All of the properties of water are based on this idea of hydrogen bonds. If you look at this picture to the right of a water strider here, what we'd say walking on water. The reason this is possible is because of the hydrogen bonds in the water. All of the molecules in that water are hydrogen bonded to each other. They have this attraction. So on the top of the surface of the water, we get this film, this surface tension, we call this. It's not really a film, but it's called the surface tension, formed by those hydrogen bonds. And if you're small enough or you have enough surface area, like this bug here, this insect, then you can walk on that surface tension. We also use the surface tension for a number of things, such as water skiing. The reason we're able to water ski is because of this surface tension. Also, if you ever skipped a rock across the water, that's the surface tension. The reason we can do that, again, is because of these hydrogen bonds. So the hydrogen bonds in water lead to some of the properties of water. The first one being the high heat capacity, then the polarities, the solvent properties of water, chemical reactivity and cushioning, among others. These are the ones that your book mentions because these are the ones that are important to us in anatomy and physiology. So let's talk a little bit about these just briefly. So the high heat capacity. A good example of this, if you've ever gone to coastal cities such as San Francisco, San Diego, if you go there during the summer, you'll notice that the temperature is around 60, 70 degrees. If you go there in the winter, the temperature is still the same. So why is that? The reason is because water has a high heat capacity. In other words, if you have liquid water, that liquid water can absorb a lot of heat, a lot of energy before it switches forms and becomes steam. And so if you go to the coast during the summer, because you have the ocean right there, even though the sun's beating down really hot, you may go inland a few, just maybe 50 miles, and it may be 100 degrees, but it's still 70 next to the ocean because all that ocean water is absorbing the heat from the sun. And so the air temperature around that ocean isn't changing very much. Then in the winter, that ocean is slowly releasing that heat that it absorbed over the summer, so it keeps that temperature at a nice, even temperature all year round. This is also important in our bodies too. We're mostly water, as you remember. And so what this means is that if you go out in very hot temperatures, your body is able to maintain homeostasis because your temperature is not going to fluctuate very quickly because the water inside your body can absorb a lot of that heat before your body starts to change temperature. So that's very important to maintaining homeostasis. The next property is the solvent property of water. This is also related to the hydrogen bonds. So I guess I should mention the high heat capacity. The reason it has a high heat capacity is because of those hydrogen bonds. It takes a lot of energy to break those so many hydrogen bonds, and so it's able to absorb a lot of heat before that happens. The solvent properties are also related to the hydrogen bonds. The reason is that because water has a positive and negative side, any sort of substance that is ionically bonded will be attracted to these water molecules. So if we look in this picture here, we have a salt crystal here. So notice the sodium and the chloride, sodium and chlorine, chloride ion. And these molecules, these red and bluish molecules here, represent water. You can see down here below the water being represented. So when you put salt in water, we all know that the salt's going to dissolve. What's actually happening is that, remember that sodium, because it's an ion, it has a positive charge. So the negative side of the water, the oxygen side of the water, is going to be attracted to that sodium. The positive side of the water is going to be attracted to the negatively charged chloride ion. And so the water molecules can just pick this salt molecule apart, and we end up with Na positive and Cl negative ions floating around inside your cup of water. Notice the polarity of the water molecule that forms those hydrogen bonds is what allows the water to dissolve these substances, and so that's what makes it a universal solvent. Okay, water is also involved in a lot of chemical reactions. We'll see as we look at the organic molecules here in a minute that our body can build up and break down organic molecules, make larger ones and smaller ones, and water is involved in those reactions. And then also cushioning, so water acts as a cushion in our body. So water is a very important molecule, and so it makes sense that our body is mostly made out of this inorganic substance. So we like to think of ourselves as solid, but we are actually basically a liquid, 60-70% water. Okay, we already talked a little bit about salts, and we saw salts there in this picture here as we were looking at how water works as a solvent. Another thing to mention about salts is that salts are made up of ions. So you may be familiar with things like Gatorade, or there's a lot of drinks that have what they call electrolytes in that liquid. Electrolytes are made up of salts. So Na positive, Cl negative, those are electrolytes, those are ions, and they are in your Gatorade or your water, and they're in your body as well. And one of their important functions is that they can carry an electrical charge because of that negative and positive charges that they have. And so when we look at our nervous system, we'll see these salts becoming important. The last one here is acids and bases, and I want to talk just briefly about these because these also are important inside our body. So our body has to maintain a certain pH. This is part of maintaining homeostasis again. And the way that we do that is we regulate the amount of acid and base found inside the liquids inside our body. What an acid is any substance that will dissociate to form H positive or hydrogen ions. So, for example, we have this substance called HCl you may have heard of, and I mentioned briefly in another lecture. This is hydrochloric acid. It is an ionically bonded molecule. When you put HCl in water, it dissociates into H positive and Cl negative. This H positive here makes it an acid. And HCl is actually a very strong acid. Bases are substances that will dissociate to form OH negative. An example, we have something called sodium hydroxide. Sodium hydroxide will dissociate in water to form Na positive and OH negative, and this becomes a basic solution. Notice something here. If you were to take the H positive from an acid and the OH negative from a base and put them together, what you get is H2O. And so what this means, if you think about H2O, it's neutral. Water is neutral. It's not acidic or basic. And so if you take an acid and you put it together with a base, you're going to form water, and that's just going to be neutral. So when we're talking about acids and bases, we have something called pH. And pH is basically telling you how many hydrogen ions or how many hydroxide ions are found in that substance, in that liquid, whatever it might be. And so this is a pH scale that we're looking at here. Notice that it goes from 0 clear up to 14, 7 being the middle. Anything that has a very low number, a very low pH, these are going to be our acids down here. Up here. Anything that is greater than 7 is going to be a base. And so 7 is our neutral point. So notice distilled water falls at a 7. As long as there's no ions in that water, it's going to be neutral. Human blood is right around 7. 7.35 to 7.45 is that pH that has to be maintained for our blood. And so that's part of maintaining homeostasis. Our blood doesn't want to go out of that. It doesn't want to become more acidic or more basic. Things that are acidic, such as lemon juice. We can put HCl on this chart as well. HCl is very acidic. Lemon juice has pH about 2. Grapefruit juice, tomato juice, coffee, etc. You can see all these things here. Something to point out here is you're going from a pH of 1 to a pH of 2. Notice that the number of hydroxide ions changes by tenfold. So the number of hydrogen ions in a pH of 2 is 10 times less than the number of hydrogen ions in a pH of 1. So it's factors of 10 here. Same thing with the basic solution. So milk of magnesia, we have seawater. Also notice here we have household bleach. Household bleach is a base, and it's very basic. We often think of acids as being dangerous. Very strong bases can be just as dangerous as strong acids. So inside our body, we're trying to maintain a certain pH in order to maintain homeostasis. Different parts of our body may have different pHs. Notice in our stomach, we have a very acidic condition in order to carry out its functions. Our blood is basically neutral, and so we're constantly trying to maintain this pH in order to stay alive. So we have both acids in our body, we have bases, we have things called buffers. And what buffers are, they are either weak bases or weak acids that allow our body to maintain a certain pH. So if things are getting too acidic, you can use a weak acid or a weak base to buffer that situation. That's going to absorb some of the hydrogen ions and make that a little bit less basic. So these are the important inorganic molecules that are found inside our body. We talked about water, we talked about salts, and we talked about acids and bases. In the next section, we're now going to focus on organic molecules.